Hello and welcome once more to my class on hyperbolic geometry. Today I'm going to start talking about fundamental groups and covering maps. If we are given a path-connected topological space, there is a very interesting relation between the fundamental group of this space based at any point and the group of deck transformations of simply connected cover of this space, if such cover exists. And in the case of Fuchsian groups, this interesting relation can be exploited to study all possible hyperbolic metrics or structures that one can put on a given two-dimensional real manifold. So in this chapter, we're going to establish two main theorems. So there are going to be two main theorems in this chapter. Namely, the main theorem is going to be that if we are given a torsion-free Fuchsian group, then it is isomorphic to the fundamental group of the orbit space of H modulo the action of gamma, based at any point. And we're going to see this theorem as a consequence of this other theorem from algebraic topology, which says that if we are given a simply connected cover of a topological space X, then the group of deck transformations of this simply connected cover is isomorphic to the fundamental group of the space based at any point. And the way we're going to use this theorem to prove our main objective here is that we're going to realize our torsion-free Fuchsian group as the group of deck transformations of the simply connected cover H goes to H modulo the action of gamma. In order to be as self-contained as possible, I am going to define the fundamental group and some basic notions, mostly without proofs, because the proofs are quite easy and you can find them in any standard book on algebraic topology. And I'm also going to talk about some basic notions from the theory of covering spaces. In order not to overwhelm you with informations and theorems from algebraic topology, I'm going to try to cover only the material that I'm really going to use to prove this theorem. So I'm not going to my treatment of the theory of covering spaces is not going to be exhaustive. Okay, so today I'm going to speak only about the fundamental group. So let's start with the basic notions. We start with a topological space, and well, if we're given 2 points, a curve from one to the other is what it should be, right? A continuous function from the closed interval to the space, connecting one to the other, right? So starting in x0, right? Sigma of 0 is x0, is required to be x0, and sigma of 1 is required to be x1. If the 2 points coincide, such a curve is going to be called a loop based at the point, or a loop in X based at the point. Okay, now suppose that we are given 2 curves, right? Sigma and tau, right? And suppose that the point where sigma ends is precisely the point where tau begins. Right? So suppose that sigma connects the point x0 to the point x1, and tau connects the point x1 to the point x2. Then, in that case, it is natural to define a concatenation, right? As a curve that goes from x0 to x2, traversing sigma in its first half and tau in its second half. Right? Okay, so we define such concatenation and denote it by sigma star tau. And here notice that we are going from x0 to x2 from left to right in the notation, right? So somehow our notation is contrary to the notation I always use for composition of functions. So if one is careful, if one is a bit careful with this notation, which is opposite to the notation used for composition of functions, there should really be no problem, no confusion. Okay, and here's the rule, right? The first half is traversed according to sigma, and of course here I have to go twice as fast in order to be able to traverse the whole sigma in just half the time, right? And same thing here with tau, and you see here is this minus one is just because just in order to rescale this interval first to make it of length 1, and then translate it so that one can actually apply tau. All right. What else should I say about this? Well, I mean, of course, one has to check that this is continuous, right? So that there is really no problem. There's no continuity in the closed open interval 0, 1/2, and there's no problem in the open closed interval 1/2, 1. The only point where one has to be a bit careful is the point 1/2, right? And then I leave this to you as an exercise to show continuity at that point, and hence continuity of the whole concatenation. Okay. Yeah. Notice. I mean, I'm defining the notion of curve as a function with this specific interval as domain. So that's why I'm careful here, because of the convention I adopted that I'm going to use only this interval. All right. We have now the notion of concatenation of curves. Another useful notion is the notion of inverse curve, and well, I'm not going to call it inverse yet, just the curve traversed in the opposite direction, right? So if I have a curve sigma, let's say connecting the point x0 to the point x1, then there's an obvious curve that traverses the same image, but the other way around, sigma minus, defined by this rule, right? So you see, it traverses the same image as sigma, but in the opposite direction, right? So it really goes from x1 to x0. And notice that here I'm being careful, and I'm not using the notation sigma to the -1, just sigma minus. Okay, and this is because it's not going to be the inverse of sigma for concatenation, but rather up to homotopy, which I'm about to define. What is a homotopy? So suppose I'm given two curves, both of them from x0 to x1. right? So both of them go from this point to x1, like this. Right? And a homotopy from one curve to the other is a sort of deformation of one curve onto the other throughout time. Okay, and I defined this notion of homotopy relative to the endpoints, and it's going to be formally a continuous function from the product of the interval with itself to the space. And I'm going to think that somehow the first interval is the time parameter. So the time throughout which the deformation takes place, and that the second interval is the domain for each intermediate curve of the deformation. All right. So the conditions are that at each time, at every point in time, the map that I obtain from the second interval to x by plugging in this s in the first coordinate is a curve from x0 to x1. Right? So this first notion somehow tells me, well, I'm starting with my two curves that go from the point x0 to the point x1, sigma naught and sigma 1. And the first condition tells me, so for this this deformation that is going to take place throughout a unit of time, for every s I have a curve from x0 to x1. Right? So somehow the whole function from the whole product of the two intervals kind of looks a little bit like I'm drawing, right? Kind of, and you see that is how you can start kind of seeing the deformation. And second, of course, the first curve, the starting curve of the deformation is sigma naught, and the last curve in the deformation is sigma 1. Right? So notice that here I'm in condition 1, I'm already asking that each curve sends 0 to x0 and 1 to x1. So somehow you see, one has a deformation, but the endpoints throughout the deformation, the endpoints, which are x0 and x1, they are not moved around by the deformation. So they are somehow anchored throughout the deformation. And, depending on the curve, sigma naught and sigma 1, such a homotopy relative to endpoints from one curve to the other may or may not exist. Right? And yeah, okay. So now notation. This, right? Sigma naught homotopic to sigma 1, and relative. You see, relative to endpoints. So this really is relative to 0 and 1 in the domain of the curves. Right? So this 0 is this 0 and this 1 is this 1, as opposed to this one, right? I mean, here, this is the time parameter. So these are not in the time parameter, but rather the starting and ending points in the interval that is the domain of each of the curves. All right. Now an exercise, and I would say this is an easy exercise, and in any case, for instance, if you are preparing a qualifying for you plan to take a qualifying exam in algebraic topology, this would be a good standard exercise. First of all, that the homotopy relative to endpoints is an equivalence relation on the set of all curves that connect my given point x0 to my given point x1. Okay, so that is, once we fix the starting point and the end point for our curves, and we don't change it through this homotopy process relative to endpoints, we have an equivalence relation. Right? So I just stress the fact that for this homotopy relative to endpoints, two curves are somehow compared with respect to this homotopy, in order to know that whether they are homotopic or not relative to endpoints, only when both curves have the same starting point and the same ending point. And for instance, if my curve sigma is not a loop, then somehow I don't compare sigma with sigma minus with respect to homotopy relative to endpoints. Okay. Second, that this homotopy relative to endpoints is compatible with concatenation. That is, if I have two curves that are homotopic relative to endpoints, so in particular, going from the same starting point to the same endpoint, to the same ending point, and same thing here, then if one can concatenate, sigma naught with tau naught, and hence also with tau 1, and sigma 1 with tau 1, and hence also with tau naught, that is, if I have, these are homotopic relative to endpoints, these are homotopic relative to endpoints, and moreover, the end point of these curves coincides with the starting point of these two curves. Then, when I concatenate this one with this one, I obtain a curve that is homotopic relative to endpoints with the concatenation of sigma 1 with tau 1. Okay, and of course here I'm aware that here I didn't write the hypothesis that sigma naught can be concatenated with tau naught and sigma 1 can be concatenated with tau 1. I didn't write it, but I did say it orally. Okay, and also taking the curve traversing the other way around, kind of traversing in reverse, taking that is also compatible with homotopy relative to endpoints. And this should be more or less clear, right? So if I have my deformation, then that pretty much that deformation also works for sigma naught minus and sigma 1 minus, right? Up to sending t to 1 minus t. So this should be expected. This other property should also be expected, right? Because let's say that you see, just kind of draw a picture. right? And then let's say that here somehow one has a deformation, right? So, and here also a deformation, and well, pretty much you can see, right? I mean, this concatenation can be deformed to this concatenation, right? I mean, kind of, you see somehow this is more or less a deformation. Um, okay, what else? Concatenation is associative up to homotopy relative to endpoints, right? So it is not true that this concatenation is equal to this concatenation. Right? And here again, I'm not writing the hypothesis that these concatenations make sense, right? So somehow condition three makes sense only when the curves can be concatenated. Right? Anyway, assuming that the endpoint of sigma is equal to the starting point of tau, and the endpoint of tau is equal to the starting point of rho. Did I say that correctly? Yeah. Ending of sigma equal to starting of tau, ending of tau equal to starting of rho. It is not always the case that this curve is equal to this curve. Kind of simply because you see, for instance, for if you go back and look at the definition of concatenation here, right? So here, notice sigma occupies half the interval. And this occupies half the interval. So each of tau and rho ends up occupying only a quarter of interval here, whereas here rho occupies half the interval and sigma only a quarter of interval, right? And actually, it's kind of only here, and here. It's only tau, the one that kind of occupies an interval of the same length, right? So one should actually expect that the equality between this curve and this curve almost never holds. Now, the homotopy between them. So of course, as I said, I'm leaving as an exercise, but you see, this you can for this it's good to draw. Sorry. To draw, yeah, the unit square. You see, somehow sigma. I said that the first coordinate is the time, right? So the first coordinate, the horizontal coordinate is the time. So the vertical direction gives me the curves. So you see, somehow sigma schematically, kind of, I have it here, and then here tau, and here rho. Right, this for this one. On the right, I have, or if you will, the last curve is here is rho, here is tau, and here is sigma. Right, and when I say here is, what I'm really saying is this for this interval of length 1/2, I use the corresponding rules of sigma for this quarter interval. is I use the corresponding rules for tau, and here the corresponding rules for rho, and similarly here. Right? That's what I mean. Okay, if you draw that somehow it comes to your mind how how a homotopy can be defined, namely, well, just connect this to this and this to this. Yeah, and then I leave the rest to you, right? So, kind of at each time s, just at each time s, just use this rescaling of this, right, and this rescaling of this, and so on. My point is that this picture should give you the idea of how the formal proof goes. Right. What else? If x naught is the starting point of sigma, then concatenating the curve with constant value x naught, so the curve that kind of starts at x naught and never moves, so it also ends at x naught, and you concatenate that with sigma, that's homotopic relative to endpoints to concatenating sigma with the constant curve at each endpoint, right? And this is also homotopic relative to endpoints with sigma itself, right? So this means that up to homotopy relative to endpoints, the constant curves are somehow function as kind of identities for this operation, right? And when I say identities, kind of identities in some category, having the points of x as objects, and the curves between them as morphisms. All right, and then also up to homotopy, this sigma minus functions as an inverse of sigma, right? Again, kind of respecting the somehow domain and codomain in this category that I just mentioned. And these are easy to prove, and drawing this kind of picture helps you to find the explicit homotopies. Okay, so this means that we have a groupoid. So what is a groupoid? A groupoid is a category where every morphism is invertible. And this groupoid, which is pi1 of x, but you see, this pi1 of x, but notice that here this notation is not the same as this other notation. Here is pi1 of x with respect to some point, and here I'm using only pi1 of x without referencing any point. Okay, the objects of this groupoid, of this category, are the points in x, and the morphisms are the homotopy classes relative to endpoints of curves in x. Right, so the morphisms from a point x0 to a point x1 are all the curves from x0 to x1 taken up to homotopy relative to endpoints. And the composition in this category is, you see, whenever they can be composed, whenever the curves can be concatenated, you compose the class of sigma, the homotopy class of sigma with the homotopy class of tau, you define it, this composition, you define it to be the class of the concatenation. And this is, for instance, this is well defined because of property 2. Right? For instance, the fact that it is a category comes from 3. Right? I mean, well, that not that it is a category, but that this composition is associative comes from 3. Right? Existence of identities for each object comes from 4, and so on. There's the fact that these identities that every class is invertible comes from 5. Okay, and this is usually called the fundamental groupoid of X, right? And it's not based at any point. It takes into account all the points. And as I said, every morphism is invertible. As I said, a groupoid is a category where every morphism is invertible. So, for instance, if X is path connected, then all the objects of this category are isomorphic, right? Because between any 2 points, there is at least one curve, and the homotopy class of this curve is an isomorphism between the 2 objects in this category. And then you can think, okay, but then this means that this category is quite simple, quite simple-minded, quite easy to understand. Right? Let's move on. But there is one point, one subtlety that makes it not so easy to understand, and it is that, for instance, when X is path connected, between any 2 points, there is not a canonical choice of curve between them. And this ultimately means that given any 2 objects in the category, we know that they are isomorphic, but there is no canonical choice of isomorphism between them. And this can actually complicate life quite a bit. But okay, so let's now define the fundamental group. Because you see, if you have a groupoid, every morphism is invertible. So if you pick a point, if you pick an object, the morphisms that the endomorphisms of this object form a group, right? Because there is an identity, the composition, the operation is associative, and every element has an inverse, right? So every morphism has an inverse. So in a groupoid, for every object, its endomorphism set is automatically a group. Well, let's take a point. Its endomorphism set, according to this groupoid, is simply the set of all curves from x0 to itself modulo homotopy relative to endpoints, right? Up to homotopy relative to endpoints. So like what is written here. And that's a group. Well, we call it the fundamental group. Right? So the fundamental group of a space based at a point is the set of homotopy classes relative to endpoints of curves that go from the point to itself, that is, of loops based at the point. Automatically, we have that in a path-connected space, the fundamental group based at one point is isomorphic to the fundamental group based at any other point. right? And actually, every curve in a topological space, every curve from one point to another in a space. So whenever the 2 points can be joined by a curve, every curve induces an isomorphism between the fundamental groups, right? And here I should have said that every curve from x0 to x1. This is missing here, and that hypothesis is missing. That this is every curve from x0 to x1 induces a group isomorphism, right? And the group isomorphism is some sort of conjugation. So somehow you see, here you have the group based at x0, right? And to any homotopy class of loop based at x0, you want to associate a homotopy class of a loop based at x1. Well, what can you do? We are starting with this curve from x0 to x1. This is my sigma. And you see, once you make this drawing, it is obvious what you have to do, right? You start with sigma minus, then go with your curve, and then apply sigma. And do this up to homotopy, right? So in particular, I'm saying that this is well defined, and it's a group isomorphism. Okay. Now it is not at all obvious that there are path connected spaces with non-trivial fundamental group. I would say it's not obvious. Now some obvious examples where some situations where it is obvious is Rn, the Euclidean space Rn, and the upper half plane, let's say, and it's because they are contractible. Right? So this is homotopically, it is a space homotopically equivalent to a point, and this is also space homotopically equivalent to a point. And that implies that the fundamental group based at any point has only one element, right? So it's kind of based at the point x0 is it's simply the homotopy class of the constant curve at x0, and same thing here. And I would say the first example one encounters of a space with non-trivial fundamental group is the circle. Its fundamental group is isomorphic to the integers. Intuitively, I would say it is clear that this fundamental group is not trivial, and that it is isomorphic to the integers, and that somehow the isomorphism tells me, you see, if I give you a curve, a loop based at the point, the isomorphism somehow tells me how many times I went around the unit circle, right? So the number of the winding number, the number of rounds, I think. So while the intuitive idea is clear, the proof is not trivial, I would say. And actually, there is one proof that uses precisely this theorem, right? So I may actually see a proof of this theorem at the end of this chapter. Okay, now for the next theorem. Right? So the next theorem, the last thing I want to say is that the fundamental group is actually a functor from the category of pointed spaces or pointed topological spaces to the category of groups. Now, what is a pointed space or what is a pointed topological space? Well, it is a pair consisting of a topological space and a point in the space. A morphism of pointed spaces or morphism of pointed topological spaces is a continuous function between the two spaces involved that takes the base point of the domain to the base point of the codomain. So a pointed space is a pair consisting of a space and a chosen point in the space. A morphism between such things is a continuous function respecting the base points, right? Taking base point to base point. All right. If I have such a morphism of pointed spaces, and you give me two loops based at x naught, so two loops in x based at x naught, if they happen to be homotopic relative to endpoints, then notice, I mean, I have my loop based here in this space, right? So somehow I have my loop. I have my loop somehow here, and I have my function. So I can apply the function to the loop, and I obtain some function here, and some function, some curve here, which would be f preceded by sigma naught and f preceded by sigma 1, which would be the curves I obtain. All right, so they are then loops based at y naught because my morphism takes x naught to y naught. Well, if my curves in x naught, if my loops I took in x naught are homotopic relative to endpoints, then when I apply f to them, I also obtain loops that are homotopic relative to endpoints. And the proof of this fact is rather easy. You see, you start with such a thing in x. Well, you see, just compose it with f, and you are done. So the proof of this fact is quite easy. But this implies, you see, that this rule is well defined. That if to the homotopy class of sigma relative to endpoints, you want to associate this class, such a thing is well defined, because if instead of sigma you take a sigma 1, you still have this result is still homotopic to f preceded by sigma relative to endpoints. Okay, so that's well defined. So I have a function from this fundamental group to this fundamental group. Exercise, that function is actually a group homomorphism, and that's very easy to prove. And the consequence is that this assignment, you see that to each pointed space associates the corresponding fundamental group, and to each morphism of pointed spaces associates this function, this group homomorphism between the fundamental groups. Those assignments conform a functor. So the fundamental group is a covariant functor from the category of pointed spaces to the category of groups. And I leave the proof of this theorem as an exercise. it is, I would say, a routine proof. And next lecture, I'm going to talk about covering spaces.